In this talk, I'm going to present Kollaps, which is a decentralized and dynamic topology emulation tool. And this has been the joint work of researchers from the University of Lisbon in Portugal and researchers from the University of Neuchâtel in Switzerland. As developers of distributed applications, we know that the network plays a huge role in the behavior of the application and key metrics such as throughput or latency. And also, we know that failures at the network level can have a substantial impact on the application behavior. Moreover, these types of failures and this variability is prone to happen, so this is the norm rather than the exception, because we don't control parts of the network, we don't control the clients, we don't control the servers, we might not control the internals of the network, so this is a very dynamic environment. And therefore, it is really important for us to be able to evaluate in a systematic way how our applications behave under a variety of conditions, and more importantly, to be able to ask questions such as what impact does halving the network latency has on the throughput of my application. Other one is what is the effect of packet loss? This is also an important question, and I'm sure you can imagine a wide range of questions you would like to ask about the behavior of your application. This is not a new problem, and there has been a huge amount of work on this topic of emulating networks. But when we look closely at the state of the art, there are a key set of limitations. One of these limitations is the scalability of the approaches. The other key limitation is the accuracy of the emulation itself, in particular under load, and finally, the dynamics of the network itself. To answer these questions, in this paper, we propose Kollaps, which rests on a key observation. From an application perspective, what really matters is not the internal state of the network devices, switches, routers, and so on, but rather the end-to-end network properties such as bandwidth, latency, jitter, and packet loss. And based on this observation, we are able to greatly simplify things we need to model, because we don't need to model the internal state of the network, we need to model only the emerging end-to-end properties. And by having a simpler emulation model, we are able to be more efficient and more scalable. And this is the key insight of Kollaps. Let's see how this works in practice. Suppose we have this target topology with one client, C1, two servers, SV1 and SV2, and two switches, S1 and S2. And because we don't want to emulate the switches, what we can do is we can instead collapse the links that we have from client 1 to server 1, and from client 2 to server 2, and so on and so forth, and replace these switches with virtual links that essentially mimic the original properties. This is the key intuition of Kollaps, where we collapse the topology into a simpler topology. And this can be done statically and with very simple rules. For instance, for the bandwidth, we take the minimum bandwidth on the path. For latency, we sum the latency, and the same can be done for the other properties such as jitter and packet loss. And this can be done in a static way and even before running the system itself. After we have this step, we are ready to deploy the application and Kollaps in a real system. And the way it works is we pick this topology described in a custom language. We assume that we have access to a series of hosts in a cluster, for instance, and we pick the application, which we assume is running in containers, and deploy it on the set of physical nodes together with Kollaps, and in particular together with the emulation manager, which is a subcomponent of Kollaps. Now, let's look at what is the role of this emulation manager. The emulation manager is responsible for enforcing the topology properties. We have one instance of the emulation manager per physical machine, and essentially it enforces the static properties, as we just saw a few moments ago, and also the dynamic properties, which we are going to look next. Well, assume this simple example, again, the simple topology, and let's say that client 1 has two applications there. And these two applications, one of them is connected to server 1 and the other one is connected to server 2. And both of them want to use the full bandwidth that is available. Of course, this is not correct, and we need a mechanism to enforce the bandwidth sharing and make sure that this is correct, in particular under congestion. However, we don't model the network elements, the switches, so we need some other way. The way you do this is through the RTT-aware min-max model, which very briefly and intuitively makes sure that each flow that is traversing a given link has a proportion of bandwidth that is inversely proportional to its RTT. Even though the model, it's simple, it's accurate enough to allow us to have a good emulation accuracy. This is not enough, of course. We need to do two more things. We need to be able to measure very precisely what is the resource usage, in particular bandwidth of each container. And we also need to enforce the emulation properties that are computed by the emulation manager. This is done through a process per container, which we call the emulation core, which is essentially responsible for performing these two functions. The emulation manager then talks with the emulation managers on the other machines, and with this we are able to build the emulation model in a fully decentralized way. Now let's look at the evaluation. We have a very extensive evaluation in the paper. Please check it for further details. Here I'm going to focus only on large-scale topologies and on geo-replicated systems. Regarding large-scale topologies, we use a scale-free network which resembles the topology we observe in the internet, and on top of this topology we perform random ping requests among random nodes. And we measure the observed value or the observed RTT with several tools, Kollaps, Mininet, and Maxinet, and then we compare the observed value with the theoretical value that we would expect in an ideal setting. And we compute the mean square error of these measurements. We do this evaluation for 3 topology sizes, 1,000, 2,000, and 4,000 elements. And we can see for the case of 1,000 elements that error of Kollaps is slightly higher than the error for Mininet, but nonetheless the error is still quite small. The interesting part comes when we start to go to higher topology sizes, namely 2,000 and 4,000 elements, where the other systems cannot reach, because again, emulating the full state of the network is really expensive and impractical at these large scale settings. So having a lightweight emulation model is key to scalability. Let's now look at the geo-replicated scenario. We evaluate Cassandra on EC2 for replicas in Frankfurt and for replicas in Sydney, and for clients in Frankfurt as well. And then we repeat the same experiment with Kollaps in a local cluster of similar machines. And what we want to observe is whether the key performance metrics, latency and throughput, are similar. The results are in this throughput latency plot. And as you can observe, the results for EC2, which is the red line, are very, very similar to the results obtained by Kollaps, which is the blue line. So this highlights that even though Kollaps is doing a significant simplification of the network state, we are still able to have very good accuracy. Let's look now at other example. And this, we pose the question, what is the impact of halving the network latency in application throughput? And in a real world, this would correspond moving the replicas from Sydney to Seoul. And these are the results. So as expected, there is a big impact on latency, and there is also a big impact on throughput. But our point with this experiment is to highlight that it's really easy to try hypothetical scenarios and check how our application would behave under these hypothetical scenarios. To conclude, Kollaps is a decentralized topology emulator. It scales by simplifying the emulation model that focuses on the emerging end-to-end properties rather than the internal scale of the network. As future work, we plan adding support for iterative experiments because now experiments are one shot. And we also plan to have time dilation properties to be able to better cope with physical resource constraints and also to make the dissemination of metadata between emulation managers more efficient. Kollaps is available as open source. We invite you to try it out and give us feedback. And we are also looking forward for a fruitful discussion in the upcoming conference. Thank you.